sir. Yes, sir. You are audible, sir.
Okay.
Yeah. So, participants, I welcome you to the final session of today's uh, of our FDP online FDP on modern computer vision. So we have with us Professor Aditya Nigam from IIT Mandi. So it is my pleasure to introduce Professor Aditya Nigam, who is currently working as an associate professor at IIT Mandi in the School of Computing and Electrical Engineering. So Professor Aditya Nigam received his master's and doctoral degrees from IIT Kanpur in 2009 and 2014, respectively. He joined the School of Computing and Electrical Engineering during August 2014 as a teaching fellow. He is passionate about teaching, and most of his last 6 years teaching is based on deep learning and its applications. So not only the concepts of deep learning, but also you can say the advanced level of deep learning. So his research interest mainly lies in deep learning, biometrics, medical image processing and its analysis, image processing, computer vision, and machine learning. He has published several papers in journals and conferences of international repute. So with this short introduction, I would like to invite Sir Aditya Nigam sir to kindly start the session. Over to you, sir.
Thank you. Thank you very much, Dr. Deepak. And I would like to thank Dr. Deepak for giving me this opportunity to teach and conduct this lecture. And really, it's going to be fascinating that so many FDPs are happening in several places. And we are also getting opportunities, and students and faculty members are also getting, an opportunity in which you can talk and you can learn several new upcoming areas into which huge amount of research work is right now carrying on. So before going to start about the session, I'm going to talk about object detection. I just wanted to know, Deepak sir, that what is the total time? What is the session time? 7:30 to 8:30?
Yes, sir. Yes, sir. You can extend
Okay,
10 minutes, 15 minutes more
5,
also,
10
but this
minutes,
is the last
15.
session.
Okay, understood, understood.
Yes,
Okay,
sir.
yeah, so I'll try to finish it on time because, anyways, uh,
Yes,
I
that will be great.
several persons are being having other commitment as well as I also have certain other things. But I will try to give you the brief introduction about object detection, and then probably we will talk about certain you know area certain algorithms by which it can actually be done. Share audio and optimize and share the screen. Start the broadcast. Let me see. Yes, it has started. All of you can see my screen.
Yes,
It's
sir.
coming.
It is visible.
Now it is visible. So now can you see my slides, that object detection?
Yes, yes, yes.
Yes. So that's the object detection. It's slightly old slides, but I find these slides to be very relevant, and these slides are being taken from multiple resources. Certain things I have written from my hand, and certain places we have taken this slide material. The material is taken from in net, but interpretation is going to be coming from me. So we all know that convolution how it's happening, and we all are aware that in all these sessions as well as everyone is now aware that if you have an image onto which you wanted to apply a filter, then this filter is going to compute certain thing locally, some information locally about a particular pixel with respect to this neighborhood, and compute a single value which is going coming out, and then you can come. This is the value which is going to talk about the information which is going to be there within this neighborhood for a particular pixel. And there are ways in which one can see that what's being learned. So these are the filter visualizations, and then one can say that these are the features that you are getting when such filters are being applied on certain images. So you can see that visualizations, and then you can see that what a network or a filter is essentially looking in the image. And then we are also aware of that pooling, that we can't work on whole image itself, but instead once you work on an image, you started to. So you need to understand one thing, that if you have an image like this of say 256 by 256, then and you wanted to make it 128 cross 128 so as to make it a smaller size, less computation, how it is possible? So 256 by 256 got converted into 128 by 128 image by using linear interpolation or bilinear interpolation. But if it is a feature map, so instead of an image, if you have a feature map, you don't do that type of interpolation. because interpolation is going to remove the features which are being there. So instead of that, if you have four things, values, value 1, value 2, value 3, value 4, we don't make from 4. If you want to make a single value, how we usually we make it by pooling. So we apply max pool onto that. So if you wanted to reduce the dimensionality, spatial dimensionality of a feature map, that instead of applying interpolation, we usually apply pooling. And max pooling is the one, it's not a democratic. Max pooling is just that 4 out of 1 is going to be given into the next, the layer, and that is the one which is having the maximum value. And then several case studies, we all are aware that LeNet and ZFnet and convolutions are, being there for a long time. But given all these new and old architectures, what are the applications where we can apply? So this is the, the crux that, okay, I got it, convolution working. Now I wanted to know that what are the areas into which I can apply. So the most important in computer vision, the several low level tasks and high level tasks. So there are several low level tasks in which the given any image, the first thing that you need to know is that what are the things, what are the objects which are there in an image. So you need to know that there is an object over here, 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 and so on. So you need to know that what are the places where we have some object, and then you wanted to know that what are those objects. So you need to localize as well as you need to understand that what is what's the object which is being there. So there is an airplane over here with a particular confidence. There is a person over here with a particular confidence. And it's a low level task. Object detection is very important. And if I say that if you know what is there in an image, then probably you can start to do some more things, and then you can talk and summarize about what is there in an image. So from an image, if you wanted to come on to a text or any type of analysis that you wanted to work or do on image, you need a low level task which can be something like an object detection. So object detection can help you to detect different objects. If you wanted to even do any type of video analysis itself, then video can actually be seen nothing as the set of images. So you have so many images: image 1, image 2, image 3, image 4, image 5, and so on. These are different set, no, a continuation in set of images. And given this set of images, what is the thing that you need to do is that you need to understand what are the objects, where are the objects, and can we track different objects along the particular frames. This is my first frame, this is my second frame, this is my third frame. Here there is an object in the next image where that object has gone. This is called as tracking. So tracking is also very important task by which you can know something about the video and its analysis. So object detection, and then you do localization, you do what is the object, and then you can somehow track that object to understand that what is happening in the video. So this is a slide in which, suppose that if I give you an image like this and then say that, okay, what is this? So you need to say that's the classification, that's the cat. So all different models that you may have seen essentially are doing image level classification. You can do LeNet, you can do Google Net, you can do Inception, DenseNet, and so many different classification models, and they can classify a given image into a different particular class. Later, when you do classification, somebody will come and say that, see, I am interested to not only know that what is this class, I wanted to know where is that object. So along with classification, you need to do localization. So classification plus localization is a computation, computer vision task. Several times it's being done. And if you do that, you need to, so what you need to give me as an output, you need to give me as an output two things. One, what's the parameter of, or the x and y coordinate of this, and the x and y coordinate of these two diagonal points essentially. Or you can give me one diagonal, one center, this corner point, and then what's the height and the width. That's equivalent. You can give me x comma y comma height comma width, or you can give me x1 y1 comma x2 y2, whatever. So usually this is being required and being utilized by most of them algorithm. So if you have a single object, a single, only object in which you are having cat or one dog or something, then this type of, thing is being said, and that classification and localization has been done. Now, in case of if you are having multiple objects, like in a single image, you are having maybe one object, maybe two objects, maybe five objects. Now the system completely changed, and I will tell you that why system got changed. It's essentially doing the same thing, but it is doing slightly different thing. And why it is different? Because instead, in an image here, you know that only one object is there, but here you don't even know that how many objects are there. So your network need to give me an output for two object or three object or five object. That is runtime. You don't know, and for every image, it is going to be changed. That is why multiple object detection, it is challenging, and its network and its training is slightly different than other type of classification in which only fixed or one or two. So it's not that only single object. I will say that if the number of object is fixed in your data. Now the object detection, when you have got multiple object, then you will say that I need to know that okay, this is my object number one, then object number two, object three, and object four, and what are these objects? So you need to give me in this case four height, height, comma, width, comma, x, comma, y, for this, for this, for this, for this, for everyone. Similarly, instance segmentation is the final form in which instead you don't want to say that, hey, don't give me an approximate rough bounding box, but can you give me a very tight localization? Can you give me such a tight localization of the dog? Tight localization of the dog or the cat or anything onto which you are interested. So this is called as instance segmentation, and for each of them, different types of machine learning algorithms are being trained. So we'll start with this is the classification and localization. And what is the input? The input has to be C class classification you need to do. Input is going to be the image, and output has to be the classification label, and the accuracy is going to be like that. What by how much accuracy you are predicting classification accuracy, that for how many times the cat class is being classified into the cat or into the dog. So that's the classification task that we all are aware of. In the case of localization, it has to do not only classification, but it has to do localization. So first it has to understand that there is a cat, and then it has to say that, oh, this is the place where is the cat, and what is that? This is the place. So in our case, it is going to do both of these things. That given any image, it has to say that this is the cat and this is the location of the cat. And the evaluation metric for this is intersection over union. Intersection over union, IOU. That is being shown in some of the slide. I will let you know. So for this ImageNet data set is being there. There are right now so many new object detection benchmarking data set, but this was a data set which was being specifically designed for this, in which there were 1,000 different classes. Classes were being there, and one image. So for each and every image, only one class and at least one bounding box must have to be there. And in such a way, there were 800 training images per class. Is at some point of time it was being considered as a very big object classification and localization uh, you know, data set. And algorithm produces five classes and bounding box cases, and if any one of them is true, so here you can see that if I have an image, it has to tell that okay, according to this, these are the five things which are being there, and where are they. So these are the five things which I assume with a very high probability it's actually Irish Wolf or Leonberg or German Shepherd or something. So five guesses it actually gives, and if any one of them is true, then it is actually being considered as a correct classification. So how we can do? Our first idea is that localization via regression. So localization via regression is some idea in which a network assumes that I am having an image, and the ground truth is also available that okay, in this image, this is the bounding box that my this x comma y comma height comma width. Assume that this x comma y is so for this, suppose that my x is say 20 and my y is say 5, and my height is say 28 and my width is say 20 or 15, whatever, some number. Right. So given this, my image is also being there, and along with that, the ground truth bounding box is also available. And if that is the thing, you can train your localization network as a regression. How? So the simple thing is that we already know that it's only single object classification, which essentially means that image is only going to have one single object. So you train a neural network which is going to predict me, an output of four numbers, and there is a ground truth for this as well. So given this image, it has to give me x, y, height, weight, and then you also have the corresponding ground truth, maybe x gt, y gt, h gt, and w gt, and then you find out the L2 loss between them, and you can train such type of localization, and localization is being trained as a regression task. So how it's being done? So usually, the recipe is that you take any type of backbone network. Now you have a bigger backbone networks. Whatever the backbone network onto which you are working on, you take that backbone network. Images are given to you. Given that image, you show it to your backbone network, and finally you got the features. Whatever the feature that you have got, you apply fully connected network onto that, and then do the classification, and you have got a softmax for this. So it's being the classification which is happening. We all are aware and have seen maybe in our previous classes that how can we use CNN models to do classification. When I say that classification and regression both, or localization and now localization is going to happen via regression. So how can I do localization via regression? So I'm having two. So whatever up to this, everything remains to be the same. And given this, I'm having two head. First head is going to do the classification, and the second head is going to do the regression. So once I train this structure first, and then I attach another head, that's the localization head. And this head is being having its losses in terms of cross entropy or whatever, because it is doing the classification, and this is going to have an L2 type of loss I just have shown. It's going to be prediction between the ground truth bounding box. So once your network actually got trained, you can train the regression head using the stochastic gradient descent and L2 loss. So first you train this network, you are trained, and then these bottleneck features actually has got some information about the classification, and now you detach this head and add this head and train this network using the L2 loss. So keep on training for some time, and later at the test time, both of your heads are being trained. This head is also being trained, this head is also being trained. So you train first of all this, and then you can train this network got trained, and later you detach it and attach it, and then train this network. And finally, from this bottleneck feature that you have got a classification head, and you have got a regression head, and both of these heads are at the runtime are with you. Image will come, you will get the set of features, and given these set these set of features, it is going to being given to classification head to know that what is the class, and regression head to know what is the corresponding object in the image. So you can see that image is there, convolution is there, and this. So for every classification head, you are going to have c number classes. Why? Because our assumption is that there are total c different objects which can be there in the data set. So we need to initially know that what are the total number of classes which are going to be there in the in your image. So this object classification and localization is assuming that we are having probably c number of classes, and and you know uh, if you are having a class agnostic or class specific, which essentially mean that for each and every class it can be trained in both ways. But for class agnostic, which is saying that for whatever be the class which is there in the image, only four numbers are going to be coming, which is saying that okay, there is an object, and these are the four numbers corresponding to that object. For the class, that is class agnostic, because class is going to be coming from this. Class specific means that you, instead of having four numbers, it is saying that suppose that there are only two classes. Suppose that two classes are cat and the other class is dog. Then according to me, cat is here and dog is here, which essentially mean that only one object is there. So for cat, it will be predicting something, and for dog, it will be saying that dog is here, but right now dog is not there, so no values will be coming over here. So class is specific, Class agnostic. Class agnostic is that one object is only going to be predicted, and class is specific. For every class, one object is going to be predicted, and uh, this regression, our classification head is going to tell that whatever the object that you have assumed or predicted in this head, corresponding class, four values of that bounding box has to be utilized at the corresponding location of that particular object. So where to attach? So the question may come that where can I attach my regression head? So somebody may say that you can attach your regression head over here, or you can attach your regression head over here. The regression head can actually be attached over many different places. It can be placed over it can be placed over here, or it can be placed over here, because this is the final feature that you have got. Then this is the feature that you have got of your classification head. Both of them are fine. Certain networks have utilized this, certain networks have utilized this, and what we have observed is that these is the place where most of the recent networks started to apply the regression head. And as I have showed that localizing multiple objects. So if your multiple object can also be localized using localization via regression, but multiple object, if you want, then it has to be a fixed number every time. If your image is having 5 objects, then every time each and every image is going to have a 5 object. Why? Because of the fact that your network is going to predict me 4 values for every object. Now if my object number is being changing, suppose that in some image I am having 4 and some image I am having 5, what can be the output of this type of network? Because network is going to give me only fixed number of output. These 4 numbers has to be given by this network for each and every object. So suppose that you are exactly having k objects in every image, the same network can actually be utilized, and instead of predicting 4 values for a single block, we will be predicting k boxes are there. So for every bounding box, I'm having 4 values, so your network is going to produce 4 into k times 4 times k different values are going to be predicted, because our assumption is that in an image exactly k type of bounding boxes are there, and for each bounding box 4 numbers has to be predicted. Now you can see that this type of network has been essentially utilized to understand a given pose. So what is the pose? So if I have an image, I assume that the pose of a person is nothing but certain very key important points which are being there localized on an image, and then all these joints and all these joint structure and its localization, if I can do, then I can somehow manage to understand the pose of a person, whether it is running, whether it's standing, what type of pose in which this person is right now. So in this case, the example is that amount or the number of joints got fixed. Number of joint got fixed. Now suppose that a person is there, I will say that this is 1 point, this is second point, third point, fourth, 5, 6, 7, 8, 9, 10. So this point got fixed, and I'm fixing it, suppose that to 20 different points. Then my network at final layer has to tell me that where are those 20 points. So 20 multiplied by all these points, that is 2, 2, 2, 2. So if that is the thing, you can again do it via regression, because for given image, ground truth is being known, because for a given image, somebody has manually annotated what are these joint locations, and given these joint locations, your network is going to take this, and then you train a regression head, CNN or deep neural network with a regression head, and at last layer, it is going to predict those location of 20 points, 20 class 4, and you got a loss, and then you train, and that have been utilized to predict that what is the pose. So localization via regression was not a big issue, and it was simple. But the point is that the other idea becomes much more important, and because of the fact, very soon you will see that why it is important. But the idea itself is can be localized, and we can localize it using a sliding window. What is a sliding window? Is again, everyone is aware that if I have an image over here, I will place something here, then here, and so on. This is actually called as the sliding window. So you are having an image like this, and then you slide it like this. that is sliding window, and so on. So sliding window is essentially going to do that we run classification and regression network at multiple locations on a high resolution image. Now the point is that if I have a big image and I am having a small network, because I can't have a very big network to see whole image at the same time. So I may apply something over here, and I do regression and classification for this, and then I apply it over here and do some classification regression onto this. Then I do regression and classification onto this, and then I do regression and classification on this. So in this way, I covered the whole image, but I apply a smaller type of network which is going to do classification as well as regression, and is telling me that what is there in the image, and then we can convert the fully connected layer to the convolutional layer and do some sort of merging, that what I have seen over here and what I have seen over here, what I have seen over here and what I have seen over here, and how can I squeeze and merge them. So sliding window, one such network was the overfit network, which is essentially doing the same thing. It will take an image, do backbone feature, and then you can do that classification as well as the regression head. Classification is having the softmax, and the Euclidean loss or the L2 loss is being utilized for the regression head. uh, the thing that the model show over here is that I'm having an image like this, which is of a bigger size. You can say that my image size is 257 by 257, but I apply a smaller size network, maybe 221 cross 221, and we first place it over here, then I place it over here, then I place it over here. So when I place it over here, I will get that, okay, there is some bounding box, and with what probability I am assuming that there is a cat, and then I change it over here. So red is the ground truth, black is the the place where I'm applying my network. So I will get this value. Similarly, I will place it over here, and then this is the fourth time I'm applying the same network. So I apply it over here, then I apply it over here, then I apply it over here. You get the fourth value, and the same network is again being applied over this side, and you will get four different values. These are telling that, okay, there is a cat, and there is a cat with a very high probability, and for each and every location, for each and every the place where I have kept my bounding box, what I have got, I have not only got the classification score, I have also got a bounding box, that where is the object that I'm looking for. So essentially, for every for every location where I placed my window, that is why it is called sliding window, I have got four probabilities and four different types of outputs that we have got. Given these four different outputs, I need to somehow do a combination, which they have done using some complex some mathematical formulation, and they can also merge it and have given that the maximum whatever be the confidence that they have got, and they have utilized it to somehow predict that, okay, this is the final output of an overfit network. They have done it efficiently, and they have utilized certain, they have shown that so many bounding boxes are going to be there for a single object, because objects multiple times you are placing different objects. Is the same thing you can see for a particular cat. We have got so many different types of objects, so we apply several methods by which many different boxes which are properly saying that there is a cat has to be converted into a single final box. So, and they have shown that if we can do it efficiently, and the efficiently mean that the fully connected things are every time going to create an issue. So they have converted it fully connected into the fully convolutional network. And once it becomes a fully convolutional network, it actually started to behave efficiently, and their performance, they have shown that their performance was also very. Now, this was the single localization, and if I have an object detection network, which can, so now the question will be that, okay, these are simple things. You are always saying that my image is going to have some objects, and the fixed amount of objects are going to be there. And if the number of objects which I'm going to predict, it is always fixed, is the localization as a regression is something that can easily be done, and we can get some results. But when I say that object detection, in which each and every object can, in an image, number of objects are going to be different. It's not going to be a fixed amount of objects always going to be there in the image. then how can I adapt to that? So that means that detection via regression that we just have seen, that regression won't work because if there are 3 objects, then 12 numbers have to be returned, and if there are 2 objects, then only 8 numbers have to be returned. So we need a network which can somehow give me, if there are 50 different objects, then 200 numbers have to be coming out. So how can I manage a variable size output? So in the case of variable size output, certain things that you need to know before we need to talk about the RCNN family is that IUU, that is intersection over union. Suppose that this yellow is the thing that you have predicted, and this red is the thing that you need to predict as the ground truth. Then the intersection is that this thing, how much amount of intersection and how much amount of union, and it is being the ratio between the intersection over union. So compute the intersection, we compute the union and intersection divided by the union. And if this value is high, that is several times being called as a Jaccard index, or other names are also being there, which is going to tell that how much amount of you know, good object detection that you have done. Similarly, non-maximal suppression, NMS, is the several times something which is being applied. I just have said that if you have an object and if you have another object, there are 2 objects, object number 1 and you have object number 2. Your networks are applying sliding window things, and because of that, a single object, instead of having only one bounding box, network is going to predict many bounding boxes. It will say that according to me there is a cat, the same cat is also here, the same cat is also here, the same cat is also here, and we apply a non-maximal suppression algorithm, which is essentially a very simple algorithm that for a given object, whatever the NMS that you have got, we will take the one which is having the maximum probability, and then anything which is having a very significant overlap with that, we keep on removing. And in this way, you are going to have the max, only keeping that bounding box which is having the maximum probability, and remaining objects which are having good amount of overlap with the same object, we are assuming that are the redundant bounding boxes which are being made and can actually be suppressed. Now again, coming to the point that now your localization or detection is going to happen via classification. So far I was saying that localization or detection is going to happen via regression. Now, so regression is having an issue that your final output has to be, very, final output is of fixed size, and that's why fixed amount of objects can only be predicted. But as soon as I wanted to predict that how there can be variable number of objects, then detection as a classification is the thing we can work on. And what is the classification? Now I will say that I don't work in that way that I'm going to search on the whole space. I have a classifier like this, and it can see an image certain portion and can tell that whether there is a cat or there is a dog, or what type of object is being there. So what I will do, I will take a big image, I will take some region into which I wanted to look and place my filter or my neural network over this, and say that tell me whether there is a cat or there is a dog. And then I place it over here, then I place it over here, then I place it over here. So I place it on multiple places, and detection as a classification is a technique in which we look out for a region, take a region, and apply a neural network onto it and say that please tell me whether it's a cat or a dog. So now it's not a regression, instead it becomes a classification. Detection via classification. If a network is being placed onto this specific region, it will say that there is a cat, yes, there is a dog, no. And in this way we can do different types of sliding window. So what type of sliding window do we apply, or what type of detection as a classification is a thing that I'm going to talk about. But the problem will be that, as you know, that you are going to apply you know you are going to apply here, and then here, and then here. So how many places you have to apply? You may say that do a sliding window and apply it on places. If you apply it on all places, it's not a single filter, it's a full neural network, a big neural network, first applied here, then applied here, then applied here, then applied here. If you do full sliding window, it is going to take huge amount. of time. So you need to know a mechanism by which someone is going to tell that, okay, given an image, certain regions are important and certain regions are not. And I can't tell that what are the things which are being there in during in that image. But somehow, if some algorithm can tell me that, okay, given an image like this, maybe a feature map like this, image something like this. Suppose that somebody can tell that, okay, this are some of the regions which are going to have very similar type of local, saliency. So this guy is telling that, okay, something is here, certain blobs which are being here. So instead of applying your neural network onto each and every, location like this, we apply it only over here, or maybe over here, or maybe over here, or maybe over here. So at least we are not going to apply for, each and every location. We are going to apply on certain important location, and certain important locations are going to play an important role. So now here you can see that I am having an image. I am having an object agnostic or class agnostic first level. First level, I need a object detector, which is a class agnostic object detection, which is going to say that, okay, according to me, there is something, 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 there is something. I don't know what are they. So first, somebody need to say that, okay, I just see a very consistent black color over here, consistent black color over here, consistent some color over here, consistent some color over here, and then it's a rough estimate of certain blob-like structure in your image, and then you need a neural network which will go and fine grain classification of these objects, and then can say that, okay, oh, there is a flower, there is an eye, there is this, there is cat, there is dog, or whatever. So for that, selective search algorithm was actually being utilized for region. So that's why this is called as region proposals. It's saying that class agnostic object detector, which is going to give me certain regions, can actually be seen as regions onto which we need to figure out what is being there. And it's going to be coming from the region proposal algorithm. Region proposal algorithm is a growing object growing or a region growing type of algorithm, which will essentially try to look for the consistency in terms of images. And there were so many algorithms were being there, and the first paper into which object detection it is actually started to utilize well for commercial task, or one can say at least a good performance started to come. That was RCN, and that is a region convolutional neural network. So I have trained a classification network separately. So you have got a classification network, that's a convolutional network, which is nothing but a backbone network which is being trained to do a type of classification. I have got a very big image. I don't know what are the objects which are being there. So I initially place it over here, then I place it onto some place, then I place it onto some place, and then I place it onto different places. Now, who is going to tell me what are the places where I need to apply my convolutional neural network is going to be coming from a separate algorithm, that is a region of interest algorithm, that is the ROI proposals that are going to be coming from selective search. That's just I have showed. This was a selective search algorithm which takes an image and tell that these are the some blob regions into which you are having certain things. And once you have got the regions, roughly top 2000 regions within the image are usually being selected. And for each such region, I apply a fine grain classification one by one. So essentially, your convolutional network is being applied 2000 times for each and every object proposal. And it actually is the same thing that you train a convolutional neural network, and whatever the feature that you have got, classification has been done using the support vector machine. It's an old algorithm, and then bounding box regression has been done using the regression algorithm, L2 loss and all. This is a working solution that's being published in 2014, way back, at least 10, 11 years back. But it was a very good working solution. And most of the time, what we have seen is most of the networks are being actually derived and utilized as some way or that's a similar type of idea, the way RCNN was being doing. And RCNN training is being done in a very simple, similar way. As I have said, that object is there, I do a final classification, and then you have got a classification head which is going to be trained. And once you have got your classification head trained, then you do the bounding box regression using then L2 loss, as I have said, and everything remains to be the same. You have got an image, then certain proposals are being given that selective search has said that, okay, according to me, there is something and there is something. So both of them are being cropped and being shown to your network one by one. And then if it's a neural network, then some final layer pool 5 features was the VGG net, but depending upon any network that you are applying, last layer features are being applied and saved in the in a disk, and then over this you train a SVM network, which is going to differentiate between the cat images and the dog images or whatever the classification, and they have trained one class binary class SVM, one SVM for each and every class. So binary SVM per class has been trained. That is saying that cat or not cat, dog or not dog, or horse or not a horse. So for every class, they have trained in that way. And then bounding box regression has been applied um, using the straightforward. So bounding box regression means that I am predicting this location, and 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 that's a good proposal. And suppose that my proposal got slightly disturbed to my left or to my right, then the DX. So regression targets are not that. Suppose that, let me give you an example, that this is the prediction that I have done, and that is 10 comma 10, and this is 10, and this is also 10. Suppose that that's my answer, my ground truth. And somehow I have predicted that this is 11 comma 20, 11 comma 12, and this is 15, and this is 16. So my difference is going to be dx, dy, dh, and dw. So what is that? So it is 1, this is 2, and dh is 6, and dw is 5. So these are the differences. I need to get things as close as possible to 0. So we apply. So regression targets are actually being the differences that are being there from the real ground truth as well as the thing that we have predicted. So it's being done using the normal regression algorithm, and they have shown that performance was good. But the main, and they have shown all possible things that, okay, it performs very well. But the biggest problem was it was very slow. It was taking too much time, and as we all understand why, because CNN was being applied too many times. 2000 times CNN is being applied. Secondly, SVM is being applied, and that is outside of the neural network, as well as the bounding box regression was using the linear regression. That was also outside of the network. So everything was very slow, and it was a very complex multi-stage pipeline. So instead of that, now they said that I am going to apply a CNN not on to the individual region onto which we are interested. I apply it on the full image data. I take this whole image and apply the full convolutional feature. So I have got, so suppose that there is an object like this, so suppose that this is my image. So I have got an object over here, some object over here, some object over here. So my region of proposal is saying that these are the regions for which I need the CNN feature. So previously, I take my CNN and apply over here, then take the CNN and apply over here, then take the CNN and apply over here, and take the CNN and apply over here. So I need to apply it 4 times. Instead of that, I will take a CNN and apply it over the full image once. I got a set of features like this. Now in this feature, because I know that what type of CNN I have applied, I can figure out that what is the feature here corresponding to this place. What is the feature here that is corresponding to this place? What is the feature that is corresponding to this location in this image? And what is the feature for this blue box that I can get it from a single convolutional feature out of here? If that is the thing, and if you can do that very easily, then instead of applying it 4 times, we have applied it only, 1 time. So instead of, if there are 2K different objects, regions, or proposals, we just apply don't apply it 2K times, but we just have applied my CNN once, and you are done. You just take this image, apply CNN once, and from that CNN, I was interested in this location, and this location. I just compute where are the corresponding features in this feature map. I take that features and show it to my fully connected network, and then do the linear bounding box regression as well as the classification. So that the good thing that they have done is that only apply CNN once, get the features, and then use a fully connected network as well as linear regression, also using the also using the neural network, as well as softmax is also being classification is also being done using the neural network. So with this faster RCNN, why it is faster? Because only computing once the only computing once the convolutional feature, as well as not using SVM, as well as the linear classification, but using everything as a single fully end-to-end neural network. So loss will be computed and everything is being back propagated. So the only thing which is happening outside of the network in this network was the region proposals. How you are getting the regions, and can you tell me that what are the places where I am interested, and I wanted to know the places where my object can be. So that is happening outside of the network, because of which it was taking time. So region proposal was something, it was an issue over there, but later, and then Foster RCN has shown that huge amount of reduction. It was training time was 84 hours at that point of time, and speed up, they got a speed up of 9 times or something. Performance was also similar or better. Several times the performance got better as well. So the solution was better, but finally they have come up with their final faster RCNN network, in which everything remains to be the same. As I have said, that the only thing which was happening outside of our neural network, but that was region proposal network. So that was the happening outside of my network was the region proposal, and in this algorithm, in faster RCNN, so they have got RCNN, they have got fast RCNN, and they have got faster RCNN. So whatever these three things in RCNN, several very complex algorithm. Fast RCNN, everything was happening inside the network except the selective search or the region onto which we need to apply. So the region selection was happening outside of the network. Now they said that instead of having that outside region proposals, or region selection, can we train another type of neural network, which is essentially being called as the region proposal network. So you are going to take an image, show it to your region proposal network, and region proposal network is going to tell you that what are the regions where do we have, there is a probability that there can be an object. And if you can do it as well, then everything right from the regions onto which I need to apply my object detector is a neural network. Then object detection is also being done using a neural network. Bounding box regression is being done using the neural network, and then the classification is being done using the neural network. So what is being done over here, and that the region proposal network, that it's a sliding window protocol. It will apply onto an image and flow like 1, 2, 3, 4 and go in the sliding window. What it essentially do is that over a particular window, whatever the thing that I am seeing, I will get a feature, and from that feature I need to tell that whether there is an object or not. Now, understand that region proposal network is not going to tell me that what is this object. It is just telling that there can be object or there cannot may not be an object. So this is actually a binary classification which is telling whether there is an object or there is not an object. And similarly, if there is an object, what is its location? So again, bounding box regression is happening. Now understand, this RPN is being trained separately and being utilized to do the final object detection. Now you can see that region proposal network is essentially a classification network which is looking for different locations and trying to estimate that whether there can be an object or not. And the other hand is telling that if you say that there is an object, then then tell me where is that object. So along with this, the concept of anchor box and other things also started to come, but given amount of time, I just don't wanted to make it very heavy, because faster RCNN algorithm takes some complexity. But what I wanted to tell is that if I am interested in this object, I will take its neighborhood, and for this neighborhood, an object can be of this type of bounding box. There can be object of this type of bounding box. There can be an object which can be here, maybe of this or maybe of this. What's the difference between these four types of bounding box? the aspect ratio is different. This is a square, this is a rectangular, this is again a square, and this is another type of rectangle. So the object remains to be at the center of this, but different types of, one can say, different types of aspect ratio boxes can be there. There can be a cat which is like this, but there can be a big box or maybe a round size object which can also be there. So because this network is not aware that there can be an object, what type of object is going to be there, so it assumes that there can be any type of object, and the object which is being here may be exhibiting five or seven different types of aspect ratio. Not only that, object can be small or object can be big. So bounding box can be like this, or bounding box can be like this, or bounding box can be like this, maybe like this, or maybe like this. So aspect ratio, so they have chosen certain aspect ratios and they have chosen certain scale. So depending upon that, if I choose two different scales and two different bounding boxes, then for each scale you have two aspect ratio. So basically you are having four different types of anchor boxes, and which is saying that I'm assuming one aspect ratio this and one aspect ratio this. And if I make it a bigger scale, then this is a second scale, but aspect ratio of this, and second scale the aspect ratio of this. So in this way, for each and every location in the image, they have said that for every location I'm going to predict that I'm going to predict four numbers, and that is telling that if there is an object, if there is an object over here, then what is the probability by which it's, there is an object, and what is its location. And different aspect ratios are, so these are different, scales onto which they have worked on: 128 by 128, 256 by 256, and 512 by 512. And aspect ratio 1 by 1, 2 is to 1, and 1 is to 2. So in this way, six different anchor box can actually be, nine different anchor box can actually be there for each and every location. And a neural network is being trained to tell, with respect to the ground truth, that given a particular location, whether there is an object which is of this scale and of this aspect ratio, or this scale, or this aspect ratio, or this scale, or this aspect ratio, and so on, for each and every scale. So there are going to be four numbers for all of them, and our assumption is that if there are total n anchor boxes, then for each anchor box, four different numbers have to be predicted by this network, that if there is an object which is of 128 scale and of this scale, then these are the four numbers. And in such way, there are total n different, which is 9 over here, n or 9 different anchor boxes, then 4 into n, total 4 into our case 9, 36 number has to be predicted. And for each and every bounding box, or n is equal to 9, so 9 different bounding box also tell me that what is the probability by which there can be an object. Once it's being there, this whole thing becomes very efficient, that a neural network will take this image and it's going to tell that what are the regions onto which we are assuming that there can be an object. Then I apply a CNN onto that, which is going to, which is, so first of all, I take an image, show it to a neural network, get the features, and on those features I apply a region proposal network, which is going to tell that what are the regions onto which I am assuming that there can be some object, and then show these to my classification and bounding box heads, just to figure out that what is the object, because RPN just only tells that there can be an object. What is the object can actually be utilized and can actually be seen by our final classification. This was so a very good object detection network. And still, if you want faster RCNN can actually run, but after that they started to have mask RCNN, which was a simpler, very simple variant of fast RCNN. It started to work very well, and then they started to come up with SSD. That's a single, I forget the full name, single shot detection, and then YOLO. You look at one. So I say that SSD was also a very good architecture. We are not going to cover, but SSD was a good architecture. But I don't see too many papers still using SSD. But YOLO is still there. YOLO version 7, version 8, version 9. I don't know what's the latest version. You look at one is something which is something like this. That here also you look the image only once, and whatever the feature you have got, you are going to utilize those features to do the bounding box regression or classification regression or whatever the thing that you wanted to do. So a big series of object detection networks were being there, but I just wanted to cover the RCNN series, which is the most famous series of networks, and most of the algorithms actually initiated and started using doing object detection utilizing the concepts coming from them. One can see that RCN was taking 50 seconds to run. Fast RCN was taking 2 seconds, and then faster RCN started to take only 0.2 seconds. So it's a huge amount of speed up with almost a similar type of mean accuracy or the mean average precision. So that was the thing that they have shown that okay, on different benchmarks, you can run our code and performs very well, and object detection can actually be initially being, I have said that the localization can actually be done using regression, but regression has their own big bottlenecks. Then object detection started to happen using using classification, and that was the correct way is being observed that if we do classification, we can do things efficient, fast, and as well as in modern day in which you are having 200 or 500 different objects in a single image, then such systems can actually be trained. I suggest you to understand and see and try to understand the upcoming new papers in object detection, but YOLO is an architecture which you definitely see. With this, I am done with my topic that I want to cover. I'm only 6 minutes um, off, and if you have any questions, you can ask. Otherwise, I am done. Thank you very much.
Yeah, thank you so much, sir, for your wonderful talk on object detection. So our participants have got it really useful, right? Participants, if you are having any queries, please write it in the chat box. Sir, they cannot actually unmute their mic. They can only write in the chat box.
Okay, so chat box, let me see. So I have got so many things. Let me read down one by one. There are so many things. Let me. Anyone has facing sound issue? No. Can you explain the fusion process and give suggestions on various ways of fusion? There are so many ways in which you can fuse. Attention is the latest way in which usually we started to fuse. So Dipankar Das, attention ke through you can do it well. Sir, interpretable AI, explainable, both are same. Interpretable AI and explainable AI. See, if you go into the definition, they are almost same. The only thing is that explanation started to happen in so many ways. Interpretation also started to happen in so many ways. So the point is
Sir,
that
these questions are from other sessions. Your questions are below.
oh, okay, okay, okay. Below. Okay, हाँ ये तो 5 बजे के बाद कहें नहीं, but when I have started, किधर से मेरे होंगे कोई can somebody tell
Sir, the
audio
last
quality?
two questions.
Acha, lost two. Thank God. I said that there are too many. No. Sir, the session is started out. If I want to use transformer, I assume that's a transformer. Transuner, I don't know, but if it's a transformer for image segmentation, what factors we can change in model to make it novel? Which part should we focus on? See, if you wanted to use transformer, there are anyways huge amount of transformers which are available for segmentation. My suggestion will be that if you wanted to do image segmentation and wanted to do new things in image segmentation, then probably use diffusion models. Diffusion models are being utilized now. It's a novel thing by which you can do some type of class, segmentation. But transformers are everything, whatever you want, it's already being done. Sir, can we merge YOLO 9 and VIT? Why you want to merge YOLO 9 and VIT? First, you take an image, apply YOLO 9 onto that, and get the objects that you wanted to know and you wanted to get. And then we apply VIT onto that. But by the way, VIT backbone can actually be used to do a YOLO type of classification. So, यही आपने लिखा था क्वेश्चन. So that can actually be done, Pradeep. So that is possible. You can use. Great session, दीपंकर ने बोला. दीपंकर मैंने आपको कोई पुराने ही क्वेश्चन का जवाब दे दिया. ठीक है, but I assume that session was useful, and I'm thankful for Dr. Deepak for giving me this opportunity. Although I was completely consumed from whole day of work, I just have came back. but I assume that the session Virender is writing, it is wonderful. Thank you very much. I really appreciate. I like teaching. That's why I every time say I was not very well prepared for the session. I just have came into the home and I've started teaching. 5 minutes back, I was in the home. I started teaching because I like. If you find it interesting, there are so many new object detection algorithms. Object detection is not my area of expertise, but I can tell you that Dino is an object detector, which actually is a foundational model. So now the everything has been converted to foundational model. And if you're interested to understand new things, Dino is really an object detector, which is a real time object detector, a new object detector, and performs really very well. So you can read about Dino as well. I'm done.
Yeah.
Thank you very much.
So thank you so much, sir, for taking out time from your busy schedule. We all know that you are a passionate teacher. So I hope participants have got at least ideas. I mean, what exactly object detection is and how it is associated with the regression problem and all. So now they can explore YOLO and several other variants foundation models by themselves. Thank you so much, sir. And we are looking forward to your second lecture on diffusion models. So
Yes. Okay.
yeah, thank you, sir. Thank you. Good night.
Good night. Thank you very much. Bye bye.
Bye. So participants, so that's all for today. We will again resume tomorrow at 4 p.m. Thank you all for joining all the sessions.